When we imagine aliens visiting Earth, we often picture an evil crew on a spaceship, scary, threatening, and weirdly humanoid. But what if aliens end up slipping onto our planet in much smaller and subtler ways, on a microscopic scale, unnoticed? Now, flip that question. When we send spacecraft across the solar system, land on distant asteroids, and bring pieces of them home, how can we be sure we aren't leaving traces of ourselves behind? Traces that future scientists might one day misinterpret as something alien. That's one of the reasons sample return missions are so fascinatingly delicate. When we venture out there to bring a piece of the universe back here, we need to touch without leaving fingerprints. And in the case of asteroid Ryugu, what came back to Earth wasn't just a handful of ancient dust, but a lesson in just how easy it is to confuse what's truly alien with what's all too familiar. I'm Alex McColgan, and you're watching Astrum. Join me today as we explore why asteroids like Ryugu are so scientifically valuable, how the Hayabusa 2 mission successfully brought home a piece of it, and the hidden threat right here at home that almost ruined the whole thing. Why study asteroids in the first place? Far more than lifeless rocks, they're really more like time capsules. You see, our solar system was created over 4.5 billion years ago. Its planets, moons, and all other celestial bodies are thought to be made from some primordial material, but it's hard to tell what that material may have been just by studying Earth rocks. On Earth, erosion, tectonic activity, and the weather modify the material's physical and chemical properties beyond recognition. That's not the case with asteroids, where this material remains largely unperturbed by time, like a window into the earliest days of our solar system. There's also evidence to suggest asteroid collisions with Earth might have delivered organic compounds to our planet when the conditions for life were just starting to emerge. Asteroids might hold insights we can't get elsewhere about the origins of the solar system and the life in it. Yet, getting to asteroids isn't easy. Most of them are found in the asteroid belt, circling the Sun in an orbit between Mars and Jupiter. A trip out there, though it has been done before, would take a long time. Not worth it just to collect a small sample. It is much more efficient to send a spacecraft to an asteroid that crosses Earth's orbit. So that's exactly what the Japanese Aerospace Exploration Agency, or JAXA, did. In 2010, the Hayabusa mission returned the first ever asteroid samples to Earth. Taken from asteroid Itokawa and weighing less than a gram, it set the stage for the sequel mission, Hayabusa 2. On the 3rd of December 2014, Hayabusa 2 spacecraft launched from the Tanegashima Space Center in Japan. The mission aimed to gain insight into the origin and evolution of the solar system, including the beginnings of life. It would do this by collecting samples from the near-Earth asteroid Ryugu. Discovered in 1999, it measures 900 meters across and comes within 195 million kilometers from the Sun, or 45 million kilometers of Earth's orbit, a quarter of the distance to the asteroid belt. After almost 4 years of travel, Hayabusa 2 arrived at Ryugu on the 27th of June 2018. The spacecraft consisted of an orbiter equipped with instruments including optical navigation cameras, a near-infrared spectrometer, a thermal infrared imager, and a LiDAR. These tools mapped Ryugu's surface, composition, and thermal properties from an orbital altitude of 20 kilometers. Soon after arrival, Hayabusa 2 deployed 2 small Minerva 2 rovers, the first to successfully land on an asteroid. Rover 1A and Rover 1B used internal rotating masses to hop in Ryugu's low gravity, capturing images and temperature data of the surface. Soon after, the mascot lander was released. Because Ryugu's gravity was too weak to pull Mascot toward it, the lander was pushed out of the spacecraft by a spring, and then free fell from a height of 51 meters. 6 minutes later, it touched down on the asteroid, bouncing several times before coming to a halt. It operated on Ryugu's surface for 17 hours, collecting magnetic, thermal, and spectroscopic data. A third rover, Minerva 2-2, was released in October 2019, but failed before deployment. Instead, it was released into orbit as a gravitational experiment before crashing into Ryugu 5 days later. Hayabusa 2 retrieved samples from Ryugu during 2 brief touchdowns in 2019. The first touchdown gathered surface samples close to the equatorial ridge by firing a small projectile. The impact ejected surface material into the sampler horn, which then funneled it into sealed containers with the spacecraft's return capsule. The second sample came from firing a small carry-on impactor on touchdown to create an artificial crater and expose subsurface material. The reasoning behind the 2 sample types was that the surface samples had been exposed to the regular radiation, micrometeoroid impacts, and temperature cycles of space, whereas the subsurface material had been shielded from this cosmic weathering, providing a more comprehensive picture of Ryugu's composition. By November 2019, the spacecraft had everything it needed. With its precious cargo loaded, it wrapped up its time at Ryugu and started the return journey home. Over a year later, in December 2020, Hayabusa 2 emerged above our pale blue dot. As it soared past us, it dropped a landing capsule containing the 5.4 grams of asteroid sample, which parachuted down to a soft landing in South Australia. NASA and JAXA are sharing samples between the Hayabusa 2 mission and the similar OSIRIS-REx mission, which returned samples of the Bennu asteroid in 2023, maximizing research potential and opportunities for peer review. As the spacecraft continued on its extended mission to another, smaller asteroid, scientists on Earth scrambled to extract and analyze this little piece of our universe's history. The heavy weight of hope was placed on this tiny asteroid sample, and it didn't disappoint. We already knew that Ryugu belonged to the C-type or carbonaceous asteroids, which tend to be found in the outer regions of the asteroid belt and contain similar materials to those from the time our solar system was formed. But what we didn't know, and to researchers' delight, Ryugu's composition was found to be very similar to a rare class of meteorites known as C1 chondrites. C1 chondrites are the most chemically primitive meteorites known and are characterized by the presence of carbonaceous material other than pure carbon, like diamond or graphite. They contain chondrules, which are small, round grains that formed in the solar nebula when our sun was still very young. It seemed JAXA had hit the nail on the head. Their mission had gotten them up close and personal with the birth of the solar system, just as they had aimed for. Today, Ryugu orbits our sun relatively close to Earth, scraping by at a distance of just 114,000 kilometers at its closest. But it didn't always call this galactic neighborhood home. Using an X-ray technique called Musbauer spectroscopy, the team put together a timeline of Ryugu's past by meticulously analyzing minute chemical changes in each sample particle fragment. What they found is convincing enough to place Ryugu's origins in the outer solar system. The asteroid's surface properties support this theory. If Ryugu had originated closer to the Sun, where temperatures are higher, researchers would expect to see coarser grains. Additionally, the grain fragments are porous. This is exactly what you'd expect to see in asteroids that once held water and carbon dioxide ice. In order for those compounds to be solid, Ryugu's parent body would have been 3 to 4 times farther from the Sun than Earth is. Research places Ryugu's formation about 2 million years after the solar system itself. Over the next 3 million years, its parent body lost its ice, leaving behind a hydrated interior and dry surface. About 1 billion years later, a cosmic impact fragmented it. Those fragments eventually coalesced into today's Ryugu. Sample analysis also showed the asteroid contains a rich mix of organic molecules. This is huge, as it implies that the fine-grained surface of an asteroid as old as Ryugu is able to shield organic molecules from the harsh environment of interstellar space. Hiroshi Naraoka of Kyushu University in Japan confirms that these molecules could be transported through the solar system and even be potentially dispersed as interplanetary dust by impacts that eject the uppermost layer of the asteroid. It seems to add weight to the hypothesis that abiotic chemical reactions on asteroids might play a role in creating some of life's ingredients. But beyond just organic molecules, one research team at Imperial College London also found something a lot more exciting. Organic matter. Not exactly life, but rods and filaments similar to the size and shapes of microorganisms here on Earth. If these were true extraterrestrial organisms, it would finally prove that the idea of panspermia, aka that life originating from elsewhere in the universe can survive the transfer between planetary bodies, is possible. But before they shouted alien, the team did what any good scientist would do. They double-checked their work. Space agencies have very tight protocols when it comes to preventing contamination. The Ryugu sample traveled to Earth in a hermetically sealed chamber and was opened in a class 10,000 clean room using sterilized tools before being stored in airtight containers under nitrogen. When scientists went to retrieve the sample to begin testing, they first performed an X-ray nanotomography analysis, basically X-ray on steroids. It allows researchers to image internal structures at scales smaller than a micrometer without sectioning or damaging the specimen. This was to check that Ryugu's sample didn't fall prey to any contamination in the process of transferring it from the landing capsule into its storage facility. The results came in. Ryugu's sample was clean. So where did the microorganisms come from? Upon arrival on Earth, the primary Ryugu samples were carefully subdivided into multiple portions in JAXA's specialized facility. Some remained sealed in their pristine state for future analysis, while others were distributed to different research teams worldwide for immediate study. This standard practice allows scientists to maximize research potential while preserving portions of the irreplaceable material. Subsample A0180, measuring just 1 by 0.8 millimeters, traveled to Imperial College London, where, despite the meticulous protocols and cutting-edge containment systems, the impossible happened. During their first observation by scanning electron microscopy, the researchers noticed something strange. Rods and filaments of organic matter scattered across the sample. Cylindrical and carbon-rich, these specimens were mainly observed on the surface of the sample, though 28% were found within porous cavities. They counted 11 rods and filaments in total, a number which rose to 147 at the second scanning electron microscopy examination 19 days later. Just to be sure, they surveyed common fabrics and fibers in the lab to compare them to these filaments. Hair, clothing, wipes, nothing seemed to match. They paid close attention to the rate of population growth and decline, and concluded that, based on population statistics, the specimens were living and had infiltrated the Ryugu rock after sample preparation. In order to examine a rock under a microscope, the sample must first be cut, ground, and polished to create a flat, mirror-like surface for examination, also known as preparation of the polished block. The research team deduced it was at this point that the rods and filaments appeared, a conclusion supported by the earlier findings of the nano X-ray tomography, which came out clean. This pointed to one explanation. The rods and filaments were likely microorganisms of terrestrial origin. Earthly bacteria had contaminated our pristine asteroid sample. The team didn't attempt to sequence the bacteria's DNA, so we don't know exactly what species it was, but it was likely a single spore of some kind of prokaryote, probably a bacillus, that started forming a colony. Luckily, the team was able to control the spread. Once they repolished the block, the microorganism population disappeared for good, and analysis could go on as planned. Despite the contamination setback, Ryugu's sample had proven incredibly valuable. Combined with NASA's much larger sample from Bennu, which weighed 121.6 grams and arrived in 2023, it had given us a glimpse into the early days of the solar system, and new findings about both asteroids are still coming to light. As we prepare for more ambitious sample return missions, including potential trips to Mars, the stakes get even higher. If we're looking for signs of life, we need to be completely certain we're not finding hitchhikers from our own planet. Space agencies do have planetary protection guidelines in place to minimize the risk of forward contamination, us taking microbes to other planets, and back contamination, setting alien life loose on our planet. And Hayabusa 2 is a great example of how space exploration is as much about the challenges here on Earth as it is about the challenges out there in space. Each mission teaches us something new about our target subjects, as well as our own methods. And despite the unexpected hiccup, Ryugu's ancient material continues to improve our understanding of celestial origins. I'm excited to see what new findings will come out in the next 5 to 10 years. Until then, we'll just have to sit tight. Thanks for watching. If you enjoyed this video, you might want to check out my other videos on asteroid Bennu. Until next time. Does life originate from stardust? Interestingly, this is something the aptly named Stardust spacecraft did not originally set out to discover, but it's a question that its findings have provoked. And it's all thanks to including the lightest substance in the world on board. The Stardust spacecraft is known for its involvement with the Deep Impact NASA mission to the comet Tempel 1. However, this was not Stardust's first mission, nor its primary one. Before Tempel 1, Stardust was out collecting data on another comet by doing something that no other probe before it had done. Its mission was to travel to the comet Wild 2, collect some of the material from its coma, and then deliver the sample intact back to Earth. And given that this would involve catching particles that were moving at over 23,000 kilometers per hour, all without damaging them, this was no easy task. I'm Alex McColgan, and you're watching Astrum. Join with me today as we explore how Stardust managed to accomplish this incredible feat and uncover what Stardust's findings taught us about cometary origins as well as our own. In the late 1990s, cometary science was still in the early stages. Although we had sent 6 probes up to visit these enigmatic celestial bodies, not very much was known about their origins. It was believed at the time that comets were foreign visitors to our solar system, older than the Sun, having been formed from the loose pre-solar grains of dust that orbit other stars, before drifting through space towards us, only to be caught up in the Sun's gravitational pull. It was believed that this theory could be confirmed by traveling to one of these comets and picking up some of this loose dust, or stardust, that surrounds them in space. By examining the isotopic composition, scientists would be able to tell if it was unusual when compared to the dust given off by our own star. However, this was a challenging mission. As is often the case, it came down to a question of speed and energy. Comets travel through the inner solar system at speeds reaching 160,000 kilometers per hour. While it was possible for a probe to try and match that speed and come up alongside it, this had to be done without needing too much fuel, or the weight of the craft would be too heavy and thus too expensive to get into space in the first place. For this mission, scientists selected a comet known as Wild 2. They believed that they would be able to get stardust alongside Wild 2 at a relatively low velocity. However, this velocity would still be around 6.5 kilometers per second, or 23,400 kilometers per hour. As you can imagine, Catching even particles at that speed would be extremely challenging. Although particles would likely not do too much damage to stardust, being too small to really impact it, it would do irreparable damage to the particles themselves. When an object crashes at 23,400 km per hour into a surface, the odds of it keeping its original shape and structure are incredibly small. Scientists would not learn much about the structure of these particles if they smashed those particles into pieces, not to mention the warping effect all that kinetic energy being suddenly converted into thermal would have on the molecular bonds involved. So, what was their solution? What was their mechanism for catching objects traveling at those speeds? Well, much like how an airbag softens the blow for you if you're involved in a car crash, scientists realized that they would need an airbag of their own, something that would not halt the particle all at once, but would reduce its speed over a longer distance, thus reducing the amount of crushing deceleration involved. For this, they found an incredible material that was basically air, solid air. They decided to use aerogel. Aerogel is a fascinating substance that was discovered in 1931 by Samuel Kistler when he made a bet with fellow scientist Charles Leonard about jelly. As you've probably seen if you've ever made it yourself, jelly is formed of two parts. Firstly, a relatively solid structure that acts like a kind of sponge, and secondly, water. When you add water to solid cubes of dense jelly, it absorbs the water and expands into the wobbly substance we are familiar with. If you were to extract the water, the solid part of the jelly would normally contract again. Kistler's bet with Leonard was to be the first one to remove all of the liquid from the jelly without making it shrink. In short, to make a jelly that was entirely filled with air, an air jelly. Without going into all the details, Kistler won his bet and at the same time invented the first aerogel. Aerogel is a fascinating substance as it is usually over 99% air and yet has the structural strength to support bricks. Nowadays it tends to be made from silica composites rather than jelly, but can be made from a wide range of materials. It is incredibly light and is, strangely enough, an even better insulator than regular air. And most importantly for stardust, when particles hit it, it would offer just the right amount of resistance to slow down the particle without denaturing or destroying it. The trails left behind in the aerogel would also be useful for scientists to spot where a particle had been captured. Stardust was fitted with a tennis racket-sized aerogel collector tray made up of 90 blocks of aerogel 3 cm thick, with over 1,000 square centimeters of surface area, which would be deployed from inside the main body whenever sampling was to take place. Stardust would also capture from the interstellar medium to allow comparisons and to learn more about the dust in our own solar system. Once it had collected these samples, it would store them on a sample return capsule, which would be fired back towards the Earth for re-entry and collection. This SRC was 80 centimeters by 50 centimeters, weighed 45 kilograms, and came fitted with an aero shield, navigation recovery aids, and a parachute. Also on board Stardust was a navigation camera, a cometry and interstellar dust analyzer, and a dust flux monitoring system, among other scientific devices. The probe launched on the 7th of February 1999 and spent the next 5 years traveling through space, passing the asteroid 5535 Anne Frank along the way, which it took some photos of. But on the 2nd of January 2004, it finally arrived at its target, comet Wild 2. And what it found was immediately extraordinary. Scientists had not expected much from Wild 2. Some NASA scientists described their expectation of it to be a rather bland object looking somewhat like a black potato. However, this is not what they found. Instead, the surface of Wild 2 was covered with spiky pinnacles hundreds of meters tall, cliffs, massive holes jetting dust and gas out into space, even on parts of the comet that were pointed away from the sun, and thus were expected to be less reactive. In short, the surface of the comet was unexpectedly alive and self-renewing. Something else was just as notable for its absence: craters. Unlike almost every other body in our solar system with surfaces exposed to space, there were no craters on the surface of Wild 2. This puts it in stark contrast to places like Mars or our own moon. Given the period of time Vil 2 is thought to have existed, it surely must have encountered other objects which impacted with it. So where had these craters gone? It shows that the comet's surface can either be self-renewing or active, reducing signs of visible craters over short time frames, astronomically speaking. And of course, during this flyby, Stardust had its aerogel collector exposed, and it was rapidly collecting dust samples. Just listen to the frequency in which dust struck the spacecraft. The samples were carefully stowed away, and upon reaching the vicinity of Earth, Stardust ejected the SRC. The angle of approach had to be just right as it was traveling at tremendous speed. If the approach angle was too low, it would just skim off the atmosphere and fly back into space. If the angle was too high, the heat would disintegrate the capsule. So it was with great relief that the DC-8 NASA airplane monitoring the sky saw it approaching at just the right second and just the right angle. The SRC landed in the Utah desert where it was recovered, everything having worked and deployed just as it was designed to. And taking the samples back to the lab, scientists learned another completely unexpected fact about Comet Vil 2. It was not a visitor to our solar system at all. Unlike what had previously been believed, Comet Vil 2 had not originated from another star. It had been born from our own. By comparing the isotopic composition of the particles Stardust collected with the samples from our own solar system, it was proven that Comet Vil 2 originated from the solar system. And contrary to what all the ice on its surface might lead you to believe, the rock at its center was formed under white-hot conditions. Chondrules and calcium-aluminium inclusions were both found among the samples Stardust collected. These are structures that only form under incredibly hot conditions and can be found in other asteroids between Mars and Jupiter. So scientists had to rethink their theory that comets formed in cold conditions at the edge of solar systems, even if they do spend some time there. Both fire and ice go into making comets. And thanks to the careful, delicate way that the particles had been collected, scientists were able to find out one last surprising thing: the amino acid glycine. Amino acids are the building blocks that make up proteins, that are vital for all living things. Although this does not mean that there was anything alive on Comet Vil 2, this does lend weight to the idea that it was from comets such as this, crashing into our Earth millions of years ago, that life's first building blocks found their way to our planet, which I'm sure you all agree offers a tantalizing glimpse into our own origins. What happened next for Stardust? As only the SRC was sent back to Earth, Stardust remained in space, and had enough fuel to visit another object, Comet Tempel 1, which is just as well as the Deep Impact mission there didn't go as planned, and you can find out more about Stardust's involvement with that mission here. After this extended mission, with all its fuel used up, it sent one last transmission to Earth to acknowledge that it was being turned off for good. Comets are truly fascinating things, and it was thanks to the incredible work of the Stardust probe and all those who worked on it that we could make these discoveries. Who would have expected that as we looked out across the wide universe, we would discover things that would help us understand ourselves better? But thanks to them, we now know life's origins might just lie in stardust. The Rosetta Philae spacecraft that visited 67P Churyumov-Gerasimenko was perhaps ESA's most ambitious mission. Launched in 2004 and arriving in 2014, it spent 2 informative years around the very interesting looking comet. Although not everything went to plan, the data that Rosetta and Philae were able to collect about comets has changed our perspective of what we understand about the formation of the solar system, and even about our home planet, Earth. The data will continue to be examined for years to come. But what have we learned so far? I'm Alex McColgan and you're watching Astrum, and together we will uncover what the Rosetta Philae mission discovered around 67P Churyumov-Gerasimenko.
67P is currently a Jupiter family comet, meaning its orbit doesn't take it much further out than Jupiter anymore. Although it was once a Kuiper belt object, which means it originated beyond the orbit of Neptune. Arriving at this comet was a revelation to mission planners by itself. So far, nothing in the solar system that has been examined closely looks anything like 67P. It's about 5 kilometers across at its longest point, and has 2 lobes, which are joined by a narrow stretch of material in the middle. This by itself was somewhat unusual, but it is also very jagged, unlike a lot of asteroids that we visited. During the course of the mission, it was discovered that the surface of this comet is quite changeable. If we look closely at the neck connecting the 2 lobes, it becomes apparent that this section is under mechanical stress. If we look at these rocks, we can see that there are fracture lines running through them. Fracture lines are also apparent from a different angle. Scientists have used models based on fracture lines found all around the neck region to determine that these fractures permeate deeply inside the comet, up to 500 meters below the surface. It seems that as the comet rotates about its axis, the 2 lobes are pulling away from each other, thinning the neck region gradually over time. Huge 10-meter boulders were observed being displaced by this mechanical stress, as well as from the volatility on the surface, sometimes by up to 100 meters due to the comet's weak gravity. This also implies that the comet is really quite brittle and porous, which is something that wasn't known about comets before this mission. As well as fracture lines, layers can also be seen, implying that during its formation, this comet was built up gradually over time. However, although it is brittle, the surface of the comet is a lot harder than expected. Scientists thought that the initial landing site for Philae would almost be soft and fluffy, kind of like a dirty snow, but this was not the case. As Philae came to land on 67P to directly interact with the comet, it found that its final resting location was solid, thought to be water ice with a thin layer of dust. Mission controllers for Philae tried to get a sample of the soil, but as you can see, Philae ended up at an awkward angle and wasn't able to get its drill into the surface. However, readings were still able to be obtained by examining the material on the craft itself, which had ended up on Philae after the bounces. Of the surface material examined, it was determined that there were 16 different organic compounds, 4 of which had never been detected on a comet before. While organic compounds do not mean life, life is based on organic compounds. While Philae wasn't able to get too many readings from the surface, Rosetta was able to get some samples of the comet by collecting some of the dust snow that was ejected away from the comet into space. One of the most impressive shots Rosetta was able to take is this video of dust particles and cosmic rays shooting off in all directions, with background stars moving in the background. All the particles are visible here because Rosetta is looking at the night side of the comet, meaning increased exposure can pick up these interesting visual elements. Throughout the mission, Rosetta collected roughly 31,000 dust particles, and interestingly, their composition didn't change much throughout the course of the mission, even as the comet became more active, meaning that the whole nucleus of the comet is likely to be consistent throughout. The dust particles consisted of complex, organic, carbonaceous material, mixed in with sodium, magnesium, aluminium, silicon, calcium, and iron. What separates this material from an asteroid's, however, is the presence of an abundance of hydrogen and oxygen. It is theorized that asteroids have been heated a lot longer than comets have due to their closer proximity to the Sun, which has stripped the hydrogen from their compositions. Comets, however, have been kept away from the inner solar system for much of their lives, meaning these dust samples are pristine relics from the formation of the solar system. and potentially even the molecular cloud the Sun would have originated from. Oxygen was an unexpected find, as it's highly reactive, and if there is hydrogen around, it will usually bind together to form H2O. Carbon and hydrogen were also detected in the comet's tenuous atmosphere by Philae. The dust particles you see here are tiny. The biggest that was collected was only 2 millimeters across. But, interestingly, it is particles just like these ones that light up the sky during a meteor shower. What these views do give us, though, are an insight to the material that formed the solar system, so that we can see where the solar system evolved from. Comets tend to be very dark, only reflecting 3 to 4% of the sunlight that falls on them, which you wouldn't expect from something considered to be icy. But actually, not a lot of the ice in a comet is exposed to the surface directly. Most of the comet is coated in this layer of complex carbonaceous dust, which is darker than asphalt. Light that isn't reflected is instead absorbed, heating the volatile material beneath the dust layer, causing outgassing of water and carbon dioxide, which also blasts the tiny dust particles Rosetta picked up into space. These colored sections in the time-lapse show exposed water ice, and as you can see, it's not a very big percentage of the comet itself. Zooming out a little bit and looking at comets generally, this is why comets have two tails. One tail follows the orbit of the comet. This tail is the dust tail. The dust tail is illuminated as it reflects sunlight. The other tail consists of the volatile material, the water and carbon dioxide that outgassed from the comet. This tail follows the direction of the solar wind, and these particles are illuminated through ionization and interactions with the charged particles from the Sun. It is often hard to see comets with your naked eye on Earth, but every so often a comet will outgas enough material that it is visible. In the northern hemisphere, the last one I saw was Hale-Bopp in 1997 when I was just a kid. What an amazing sight it was. You guys in the southern hemisphere have been a bit luckier with comets. You've had Comet McNaught in 2007 and Comet Lovejoy in 2011. Going back to 67P, there was one other very big reason why the Rosetta Philae mission happened in the first place, and that was to see if water on comets is the source of water on Earth. Before this mission, the theory was that Earth was bombarded by comets early in its development, back when the solar system was a lot more chaotic. Considering a large portion of comets are water ice, these could have given the surface of Earth the water we enjoy today. But, as it turns out from Philae's findings, this was not the case. Scientists were able to determine this from the water vapor's deuterium ratio to hydrogen, which is significantly different from Earth's. Deuterium is an isotope of hydrogen with an added neutron. The ratio of deuterium to hydrogen in water is key to determining where in the solar system an object originated. Here's Earth's ratio, and here is 67P's. As you can see, they are very different. Only two comets have had their water vapor measured for deuterium directly, 67P and Halley's Comet, and neither suggests that comets were the source of water on Earth. Instead, this data gives more weight to models that suggest asteroids are the source of water on Earth, even though their water content is generally very low. If this is the case, Earth had a rough time during its formation. Rosetta and Philae were also equipped to detect if the comet had a magnetic field. Initially, scientists thought they had discovered the presence of a magnetic field on the comet, the hum of which they converted to audio sound, and this is what it sounds like. However, it turns out that this was not the result of a magnetic field, as Philae could not detect the presence of a magnetic field on the surface, but rather, this sound is the solar wind's interaction with the comet's atmosphere. In fact, because of this interaction, the atmosphere and comet nucleus are completely devoid of any magnetic field, which is called a diamagnetic cavity. Rosetta finished its mission by crashing into the surface of the comet. As the comet was going further away from the Sun, there was no guarantee it would have enough power for its heaters. So in order to maximize the science gained, mission controllers commanded it to perform a controlled descent into the comet. During this descent, it took multiple images, which you can see in this time-lapse, providing better resolution images of the comet than ever before. Until finally, it hit the surface and all communication was lost. Between Rosetta and Philae, they have opened our eyes to what the solar system was like during its formation, and have provided data that has and will yet lead to many discoveries. Here's hoping for many more missions like this one in the future. Space exploration is getting exciting.
When it comes to astronomy, the approach of poke it with a stick is usually not a very viable option. You cannot poke stars with a stick, and not much can normally be learned by poking planets. However, if your stick is actually a high-tech sample collection device, and you target a cosmological time capsule composed of loose regolith and dust, suddenly we have the setting for the largest and most scientifically advanced stick poking in human history. And with the OSIRIS-REx spacecraft's mission to the Bennu asteroid, that's exactly what happened. I'm Alex McColgan and you're watching Astrum, and today we continue with our third look at the OSIRIS-REx program. In this video, we explore the moment of truth, the culmination of a journey that spanned 4 years, the first time in history a US spacecraft poked an asteroid. If you watched my other videos on this topic, you will remember that the OSIRIS-REx, or the Origins, Spectral Interpretation, Resource Identification, Security, Regolith Explorer, is a NASA-developed spacecraft that was launched in 2016 with the mission of collecting and then bringing home to Earth a sample from the near-Earth asteroid known as 101955 Bennu. This mission is an important one, as Bennu is an extremely old asteroid. It is thought to have been around since the birth of the solar system, and as such is a treasure trove of information about the solar system's formation, and maybe even the origins of life. However, while missions have photographed asteroids before, and have even collected stardust from the tails of comets, this was the first time a US spacecraft would have ever traveled to an asteroid to physically collect a sample from its surface. NASA's goal was to collect a 60-gram sample of regolith and dust from Bennu's surface. It would do that by entering Bennu's orbit and slowly descending. It would be careful not to disturb or contaminate the asteroid's surface by using its thrusters, but would drift gently down, extending its long touch-and-go sample acquisition mechanism, or TAG-SAM, as it did so. Then, at the moment it touched the surface of the asteroid, it would release a burst of nitrogen gas from its arm, kicking up dust and materials, which would be captured in its sampler. OSIRIS-REx would then return home with its sample. However, that mission was not as simple as it may sound. Bennu is a relatively small asteroid, only about 490 meters in diameter, which meant that there was very little gravity. While scientists had previously mapped out the rough shape of Bennu to a surprisingly high degree of accuracy using radar imaging, this low gravity had led them to believe that Bennu would be made of relatively fine materials. This was not the case. Bennu was covered in large boulders, some of which were 58 meters across. As such, there were limited places where OSIRIS-REx would be able to touch down to collect its sample. And so, OSIRIS-REx spent over a year, 505 days, circling Bennu and mapping out its surface, choosing the best location for its system-spanning pogo stick hop. After careful deliberation, NASA had decided on potentially 4 sites for the sample collection: Osprey, Kingfisher, Nightingale, and Sandpiper. You might notice a bird theme here. Bennu itself was named as the result of a contest run by the University of Arizona, the Planetary Society, and the Linear Project in 2012. In it, more than 8,000 students submitted name ideas. The winner was a 3rd grade student who wanted to name the asteroid after the Egyptian mythological bird Bennu, because he thought that the OSIRIS-REx's tagsam arm looked like the graceful extension of a heron's neck, just like the Egyptian god Bennu, meaning it was named after the craft visiting it rather than the shape of the asteroid itself. NASA seems to have kept with this bird-like naming convention. In the end, NASA chose the Nightingale site for OSIRIS's landing. The site was set in a crater that seemed to be relatively young and clear of rocks, which came with numerous benefits. Not only would landing be easier, but the recently exposed material beneath Bennu's surface would likely be an accurate reflection of the asteroid's internal workings. With the site selected, OSIRIS began its slow descent. However, it did not rush in with a single try. Instead, it did practice runs. The first took place on the 15th of April 2020. OSIRIS-REx approached the asteroid to a distance of 65 meters before activating its thrusters and rising again. Everything worked perfectly, and its thrusters worked just as intended. Satisfied with this run, scientists sent it in again. On the 11th of August, OSIRIS-REx approached at a distance of 40 meters before once again rising, slowly darting forwards and backwards, but drawing ever closer. And on the 20th of October, this heron look-alike went in to strike. Using onboard computer systems to plan its trajectory and perform its operations, as the lag time for signals from Earth rendered real-time remote control of the spacecraft impossible, OSIRIS slowly reached out to touch the surface of the asteroid. It raised its solar panels in a Y shape to keep them out of the way and protect them from any loose dust that was about to go flying. It reached out its arm to land. It touched the surface. And then, surprisingly, it kept going. When I think of the surface of asteroids and comets, I imagine them as firm and hard enough to stand on, as you might see in films such as Armageddon. But the truth is that, particularly for small asteroids like Bennu, their low gravity means that their mass is only loosely held together. What looks like a stable surface is actually loosely held material interspersed with pockets of nothingness, gaps that mean Bennu is so easy to sink into, if you stepped on it, you'd likely vanish inside of it. Like stepping into foam, OSIRIS-REx's arm sank almost half a meter into the surface of Bennu before the thrusters arrested its fall. Furiously activating its nitrogen gas burst, OSIRIS blasted a hole in the side of the asteroid. What was expected to kick up a little regolith and dust displaced over 6 tons of loose rock, as all that material, so loosely held together under Bennu's tiny gravity, was catapulted in all directions. OSIRIS-REx's thrusters went into overdrive, burning the most they had ever burned on this trip to pull them away from the expanding cloud of dust. Of course, this was all pre-programmed. NASA had planned for this, although perhaps not to this extreme. OSIRIS-REx had just made a new massive crater in Bennu. Upon getting away from the asteroid's surface, OSIRIS-REx checked its haul. It had hoped for 60 grams of material. Instead, it found it had collected somewhere between 400 grams and over 1 kilogram of material. So much material had been collected that a rock got stuck in the flap that closed the sampler's head, causing some small amount of the material to get lost. However, OSIRIS-REx succeeded in transferring the sampler head to a sealed container built into it. Its mission had been a huge success. For a time, OSIRIS-REx stayed watching, flying over the asteroid to image it and see the outcome of what it had done. The surface of Bennu was different now. Even larger materials had moved far. Just look at how far this boulder was thrown, around 12 meters across Bennu's surface. However, OSIRIS-REx couldn't linger forever. Its sample needed to get back to Earth, and so, after performing one last flyby on April 7th, 2021, it began a long journey home. And there we have it. Right now, as of the release of this video, OSIRIS-REx is making its way back through the void of space. It is thought that it will arrive back around Earth by September 2023. Once it reaches Earth's orbit, it will release its sample, which will fall through our atmosphere to land in the Utah desert, where it will be collected and examined. This will mark the culmination of an incredible scientific exercise, collecting a sample of an asteroid and returning it back in pristine condition to Earth. But as for OSIRIS-REx itself, this mission was only the beginning. Having captured a sample of Bennu, this Egyptian heron will be off to slay a new beast, Apophis, the Egyptian serpent of chaos, destroyer of light and order. Or more accurately, the Apophis asteroid, a 370-meter diameter asteroid that is believed to be passing within 50,000 kilometers of Earth in 2029. Let's hope that the asteroid does not behave in a way that's too in keeping with its Egyptian namesake. Either way, OSIRIS will be heading off to investigate it, once again using its thrusters to kick up material from the asteroid's surface for analysis. To reflect this extension of the mission, OSIRIS has been given a new name. No longer is it OSIRIS-REx, it is now OSIRIS Apophis Explorer, or OSIRIS Apex. With a name like that, perhaps its greatest discoveries are yet to come.